Okay, thank you for inviting me here, and thank you for staying until this late. So, good evening. My name is Wang-Zhou Dai. So I just graduated from my PhD and joined Imperial in this April, actually. So I'm a freshman here, and now I'm just a postdoc. So really, it's my honor to be invited here to have this chance to share my recent research, actually. So tonight I will talk about the abductive learning, so which is a framework that we proposed, try to bridge in the machine learning and logical reasoning. So first, I want to review the machine learning and machine reasoning, what happened in AI field so far. So we know that machine learning has now become very popular, and it seems to be very, very powerful. It achieved a very, a great success in many fields. For example, in image recognition. So this is, I think, so it's in 2012 when deep learning started to, surpass human beings' performance on image recognition. Then deep learning and machine learning became really hot, and it re-entered people's life. So it's really a milestone. And also, it performs very good on speech recognition. So these two kind of applications, they have a common characteristic. So what is it? It's mapping some sensory information into one concept or multiple concepts. Like if you inputting one image, then it tells you, or it learns to tell you whether it is a picture of Africa, does it contain a lion, or does it contain a huge grassland, such things like this. So this is what machine learning so far pretty good at with. Now, machine learning is actually also have some, it's some limits that which it is not very good at, such as answering questions or like learning some simple relationships. So in this example, an input is an image, and then a question is associated within with the image. And then AI should answer questions from, by considering or input this image. And this task is actually providing some examples, composed by some small piece of shapes on an image, and trying to learn some simple relations. For example, so here we have there is some relationship called same, and this one is a false example because these two shapes are different, and this one is true. So these are the examples. The target is to learn this kind of relationships, and it turns out machine can use quite a lot examples to learn this kind of simple relations. In this kind of task, I wouldn't say machine learning is very good at, but it's actually somehow they still manage to have a comparable performance like human. And there are still some problems that machine learning are totally incapable of. So, for example, this is a new data set published in 2018. So it's basically a bunch of dialogue here. So some teacher is asking questions or saying some facts. And then the machine is trying to learn from this dialogue and try to answer questions from natural language. And from the results so far, the performance of machine is still way behind of human performance. And another example is a data set that DeepMind has just published. So this is some mathematical questions most of them are like in the high school level. So the task is trying to answer these questions by reading them. So deep learning has also been tried on this kind of problem, but still it doesn't have a good performance, specifically in some types of these mathematical problems. So, well, these tasks that machine learning are not very good at is somehow different to the task that they are good at. So these tasks actually are asking us to reason about the context, to reason about the input we have. So it's actually, we have to build or output one concept based on some complex relationships between the objects or inside of the input, like the dialogue. The first sentence, second sentence, and following sentence, they have some complex relationship there. And also in the mathematical problem, the inputs actually have very well structured problems, like these mathematical equations or like these expressions. So that's why machine learning is not, why machine learning is not good at this kind of tasks. So if you think about it, machine learning so far is actually a modern rephrase of curve fitting. So curve fitting have existed a very long time. So when Newton invented the gradient descent, that time people is already trying to use some mathematical problem to do curve fitting. And then Gaussian invented the least square regression and all these kind of tasks, all these kind of approaches. And machine learning so far is now just trying to do this. So give some training data here, x and y. The input is x and output is y. And machine learning is trying to minimize this kind of loss. So the L here is the loss function, and N here represents the entire training data set. So machine learning so far is trying to fit a simple function here, which minimize the imperial risk. So this is how current machine learning solving the perception problems. And we can see that this kind of setting is quite good for modeling perception like tasks, because the input and the output is directly linked by a very simple function, like interpreting some things, some objects from the image, or understanding the words from a speech, something like this. So in this kind of form, the machine learning doesn't have any explicit modeling of reasoning. So this is why, at least I think, why machine learning today is not very good at reasoning. So will it bring any problem? So now more and more deep learning people or machine learning researchers are trying to use this kind of paradigm, which is using the empirical risk minimization paradigm to deal with reasoning problem. So for example, so this is when you try to make human recognition a pure perception in a human recognition in a pure perception framework. So given a small perturbation here, like a color block, then deep learning model or deep neural nets can be entirely fooled. And also, actually, in many years ago, like in 2015, 2014, I think, researchers already find this kind of problem. So given an image, so this is an image of panda, and deep neural net can give a 57% confidence saying this is panda. Then add a very small noise here and resulting a new image that there is no difference between them. But it says this is a given with 99% of confidence. So this is why, this is when you're treating reasoning as perception, it brings a lot of problems. So this kind of task shouldn't be directly like mapping from pixels into some high-level notions. So if human beings are doing like recognizing whether this is a man, then we directly see whether there is a face, whether there's a leg or anything that belongs to a human, and then we can say this is a human. Also, for this kind of images of animals, we just try to recognize the characteristic of these animals, and then we can reason about, okay, so panda have really black eyes and have black and white furs, and then looks like looks like a big cat, then it is a panda. So this kind of reasoning happens in in our everyday life. And also, treating reasoning as perception brings another problem. So, it just like this monolith is from the movie 2001. So the deep learning model, or most of the statistical learning model until now, is just like this black stone here. And we are not pretty different from these chimpanzees or very ancient humans. We cannot understand what happened inside of this block. So if you read the novel, actually, instead of the movie, you Arthur Clarke talks more things about this monolith in his book. So this is actually a screen, and it can show a lot of images and videos in the night. That's when our ancients gained some intelligence from this kind of block. So this is some kind of like the machine learning or deep learning to us, at least to me. So it's so fancy. I can see a lot of things from its output. But what happened inside, I don't know. So what does this, what does it bring any problems here? So it's majorly two things. So firstly, we cannot tell anything we know to help machine learning model. So it's very difficult. Like the previous talk, we have to design some kind of some domain-specific language, or we have to design all kinds of mathematical equations or expressions like loss functions, regularizers, and to encode our knowledge to teach these machines how to learn. And also, another problem is that we can hardly understand how does this machine reasons, or how does they understand this world or this problem. So it will be very difficult to interact with them or understand them. So this is really bad. And now more and more people are trying to, do some study on explainable AI or interpretable AI. It's trying to solve this problem. But in fact, I think the real gap is here. So we should not treating reasoning as perception. So the entire foundation of what we have done before is not appropriate for modeling reasoning problems. So machine reasoning is actually the very first task in AI. So Simon and Newell, so these are two pioneers of artificial intelligence. And this is their paper about logic theorists. And this is the first talk on the Dartmouth conference. So the first AI conference, and this is the first AI program. So what does it do? It uses, it can reason or it can deduce some theorem based on few axioms. So it can prove some initial theorems from the book called Principia Mathematica. It's a book from Russell and Whitehead. So the first problem they try to do is do reasoning in AI. Actually, the following years of machine reasoning developed as symbolic AI. So what they have done, like general problem solving and automated theorem proving and Boolean satisfiability, expert systems, and then logic programming, inductive logic programming, probabilistic logic programming, and constraint logic programming, answer set programming, all these kind of things belongs to this category, machine reasoning. So they really got a successful achievement in the 1980s or 1990s. And at that time, like Alan Newell and Simon, they really be very aggressive and give a statement like this. It says, a physical symbol systems is already enough for any general intelligence. So they think symbolic AI is already capable of solving all kinds of intelligent problems. However, as we know now from 1990s until now, symbolic AI become a very unpopular area. This is because what they have did requires a lot of human power to write rules or incorporate the so-called expert knowledge and trying to encode expert knowledge in AI and make AI by programming. So this is the problem. And also another very serious problem is like 40 years later. So these are two papers from the communication of the ACM. And 40 years later, in 2015, Stuart Russell, so he's a another artificial intelligence professor. So he said the symbols actually doesn't naturally existed in the data. So that's why he called the real object seldom wear unique identifiers, which means when we are given some image or some sound waves, do we really have any symbols in them? So previously in symbolic AI, we assumed that all these symbols are provided in the data. They existed. But in fact, does these symbols exist? We do not know. And this is the biggest, the biggest problem of symbolic AI. Now, if you think of the past, the symbolic AI and machine learning or perceptual-like AI is actually developed separately. But does they really separate? So to answer this question, we can, we can take ourselves as an example. So these are some pictures. Can you recognize any face in these pictures? It's very straightforward, right? So these two are eyes, and this is a mouth, and like these are two eyes, and this is a mouth. So actually, we can recognize face in all kinds of things. So this is actually the reasoning. What we are thinking about face is that a face must have two eyes and have a mouth. So this is some kind of symbolic reasoning, right? But using this kind of symbolic reasoning, we really have some, they really have some effects on our perception. So it really makes us thinking these pictures are really faces. And also, last week, I went to the Natural History Museum, and I saw they have an exhibition of moon there. So this is a picture I took from there last week. So if you recognize this picture, I can enlarge it. So this is the moon. Where does the sun existed? So where's the direction of sun? Do you have any here? This place? or this direction. So it's actually very confusing. When I looked into this model, it's really confusing. So if you can see the craters here, so there are some shadows and some highlights here. But in this side, the shadows and highlights actually are actually located in the entire opposite directions. So this is why this picture really confused me. I think it also confused you as well. So we have some general background knowledge about what does a concave shape looks like in a light, under a light source. And we also have some background knowledge about how does a convex object looks like under some light source. So when they combine together, maybe these are holes and these are mountains, or these are mountains, these are holes. Depends on your assumption, where does the sun existed. So this is another example to show you that reasoning and perception actually happens together when we, doing cognition, when we seeing things or in our cognition. And this is pretty well known in cognitive psychology. However, in machine learning, we still haven't got anything to model this process. So what I am trying to do is to bridge machine learning with reasoning. So previously, we have some raw data and trying to build an end-to-end model and give a final concept. It really good in some kind of tasks. However, it doesn't have any reasoning explicitly modeled here. So what we are trying to do is to make reasoning a part of our recognition or our perception. So here we have some perception model can do some simple perceptions, like from an image we can recognize some like sun, river, mountain, or fog. And then we can use this primitive as symbols and do abstract high-level reasoning to tell us whether this is a picture from midnight or this is a picture from like morning or any other time. So this is more close to the human computing or human reasoning paradigm. So the real question is that how does these two things, combine together? So previously we used end-to-end learning, and this is quite easy because all these models are continuous. We can have some error propagation techniques like backpropagation, or we have like EM approach, or we can use gradient descent. So as long as the problem is continuous, the model is continuous, then we can directly apply some mathematic techniques and try to fit this continuous function or continuous curve. However, here it's actually entirely discrete. And the problem here is actually we have to do some combinatory search. And we do not have any gradient here. But here, perception, still we have some gradient, we have some continuous function. We do not need to understand what kind of reasoning happened here. We just want to build maybe a neural net to recognize simple symbols. So the main question is how to combine the continuous function-fitting mechanism with a combinatorial reasoning mechanism. So I have been working on this topic for many years. So even I started this topic when I was a master student. So I have tried a lot of things, and I've seen a lot of works on this topic. So many years ago, actually, this is when in the beginning of the 20th century. So like a lot of logicians trying to make logic, which is a discrete system, continuous. So they invented multi-valued logic and also fuzzy logic. But they have some problem. They have a really bad problem. that how to define the implication. So implication means if A happens, then B will happen, right? If, then. This is a very simple rule. And in in first order logic, this is quite straightforward. If A is true and B is true, then this rule is true. The implication holds. Otherwise, it doesn't hold. So, like this kind of things. But if you make logic continuous, then actually there are multiple ways to define the implication here. Like Gödel, Lukács, every logician have their own ways to define. They do not reach any agreement. So this is the biggest problem. And then there are statistical learning and probabilistic logic programming. So most of them are trying to model logic problem as a probabilistic model. So for example, probabilistic graphical model. However, if you want to do inference in this kind of probabilistic models, then you have to introduce some independence assumptions. And also the complexity of inference is very, very big. So you have to introduce some unnecessary assumptions like pseudo-likelihood or mutual independence, which makes reasoning quite, different. So like recursion or any loops in the graph will make the inference harder. So also there are some researchers are trying to model symbolic reasoning by neural nets. So they call neuro-symbolic learning. What they do is trying to use word embedding, like embedding the symbols as vectors, use distributed representation, or use fuzzy log operators like here, the implication or and, or these kind of operators to make symbolic computing continuous and also represent them in a distributed space. So what they have, really, they have some good applications, some database or some areas that have simple relationships. However, with this kind of embedding representation, it's very difficult to extrapolate the representation or the model in new domains. For example, I embedded like one word, like neuro here, embedded as a vector. Then I changed the spell of neuro, or maybe some people tend to simplify the spell like neuro in N-E-U-R-O. And then this word hasn't been embedded ever in the vector space. Then the neural nets entirely, they cannot recognize this kind of word. Then the entire system fails. So this is the biggest problem for them, the extrapolate generalization problem. So what I am thinking is trying to make neural nets and logic, they can play their what they really good at. So what I have tried to do before is trying to introduce some kind of abductive reasoning here. So we have some real first order logic rules here, and trying to tell like this is the example. So we in representation learning. So the target is trying to learn some features, and these features should be good for training a classification model. So this is when we do not have any knowledge, then the features being learned is actually completely random. It's actually doesn't have any semantic. But if we have some knowledge about how human writing these letters, then we can actually make them really learn strokes. And this is how we add the background knowledge or first order logic reasoning knowledge into the learning system. It really helps it to functions as what we did. So this is the first trial of my test of abductive reasoning. So now, what is abductive reasoning here? So abduction is actually what we call the Sherlock Holmes way of doing inference. So if you're familiar with Sherlock Holmes, so he claimed the way he make reasoning is called deduction. He called the science of deduction. However, this is wrong. What he did is actually abduction. So what is abduction? Abduction is trying to explain some specific observations from your background knowledge. So if we take it here, so this is implication, or we say it's entailment. So if B and H holds, then we can get E. So the E here are observations. And here, Holmes is trying to actually, when he saw a crime scene, and he has some background knowledge, like if the body was, beaten after death, then the bruise in the body could look quite different. So when he saw some bruise on body of Bob, then he know that Bob might got this bruise after his death. So this is actually some kind of explaining what you see by considering some background knowledge. Like we can see this picture again. So this time I flipped this picture. So how do you interpret differently? Can you find any other explanations? So what we have here actually are very high level and symbolic background knowledge. So if the object here is convex and the light comes from one direction, then the highlight should be on the same direction of the light source. If the object is concave, then the direction of light and the direction of highlight are opposites. So these are the basic background knowledge we have. So based on this kind of background knowledge, actually what we do, we can generate multiple hypotheses. I think most of you now can see the light source could also be here or be here. So this is because we can explain the observation, these caves or these mountains, by considering this kind of background knowledge. So that's why we are using our high-level reasoning towards knowledge to shape the way we're perceiving this image. So now this is the basic idea of abduction. And next I will show you a more specific example. So that's why that's the motivation of my work and how I get inspired to do this work. So here is a very interesting human example. So this is a Maya temple. It's called Temple of the Foliated Cross. And this temple have a lot of this kind of tablets. And these tablets here, you can see the characters. You can see actually the blocks here. These are some glyphs. And these glyphs actually formulates, is actually a very small essay. It contains a calendar in this initial, and then it tells the date when this tablet was carved, and then the character here says what things happened in this year. So when they first got this discovered, it's really a myth for the historians. How can we read from this? Now, then actually some of the historians have some background knowledge here. So these are the calendars, and these calendars have some specific structure. Like here is the initial, and here is a time period, and these are the date. So there is some calculation happened in here. It's like this initial plus a time period equals to an exact time. And this is the structure of the calendar. And then how to calculate these numbers. So these first column are numbers. The second column are units. So if you multiply the first number and the units, and you actually get a very specific time period, like this could be a year or a week, and then day, something like this. So this is how you calculate the numbers. And then the problem is that each number actually have multiple kinds of representations. Like 1 here, you can see they looks pretty different. And the 9 here, yeah, you can see the variance here. It makes really difficult to recognize if you want to train a neural net to do this. So what does they do? So this is a graph I read from one book. So here the red, the blue, and the red. So the 2 red should belongs to 1 character according to this book. And these ones should be different to the red ones. And the other characters, actually, they already know. So some people correct the numbers, part of these numbers before. So what they do is trying to do this kind of calculations. So they try to substitute this, make some guess. So say, if this is 9, then we can substitute the first one as 9 and this one as 9. So in the yellow block, which is the date here. And then we guess the blue one. We can enumerate from 0 until 20, because Maya numbers are 20 based. And then they can do some calculation here. The calculation actually can, if you substitute these numbers, then you can get a result. And these are results that you interpreted from the image. And these are the results you calculated from the equation. So the historian did a lot of trial and errors. And then finally he found that this one is really good because the calculated result and the interpreted result are the same. They're consistent. So this should be how we interpret these glyphs. So the red one should be 1 and this blue one should be 4. So this is how humans try to learn from this kind of problems by doing some trial and error searches. And this is actually a very typical way to do this. And we are trying to do this, actually we did this every day. So what he tried to do is, first he have a perception power which interprets glyphs into some numbers. And then it uses abductive reasoning. So he tries to explain the observations, the glyphs, by considering some background knowledge. So his observation is really simple. These equations on the tablets must be correct. They cannot be wrong. Otherwise, I think the man who carved this one already been killed by the king. So these equations are correct. And also he has some background knowledge about the structure of this tablet and how to calculate in Mayan ways. So like 20-based additions here. Then he did a lot of trial and errors until the perception results and the reasoning are consistent. So the calculation here are symbolic reasoning, and perception here are actually raw data perceptions. So this is how we come up the idea of abductive learning. So this part should be very quick because it's totally, we try to mimic the way of the historians did. So the input is quite simple. So the inputs are images, like raw data. So we have an image and a label. So the label are true or false, a binary here. And we have some background knowledge. So the background knowledge actually, is based on some primitive symbols, just like the numbers we had before in the Mayan examples. However, we do not know whether the inputs have which kind of primitive symbols. So the Y here is totally different than the symbols here. The output is trying to build a perception model as well as a knowledge model. So here the perception model can map from the input into the primitive symbols, like from the glyphs into numbers. And here the knowledge model should do some reasoning. So from the perceived symbols, we can do some reasoning and really get our output like this equation is true or this equation is false. So now we can see some example. This is a simplified task. So the input is still an equation. And the equation actually should be interpreted first into some primitive symbols. And then we can have some ways to reasoning about whether these equations are correct. So the task is trying to, so before training, we have untrained CNN here, convolutionary network. And also we do not the rule. Actually, this could be any kind of addition rules. This could be addition, could be like logical XOR, logical AND, logical NOT, or anything like this. So the target is to train to learn the perception and reasoning jointly. We have to learn this model, which interprets it from here to symbols. And also we have to understand what kind of computation happened here to really find out what kind of additions here and get the real labels here, like this is a correct equation or this is a wrong equation. So the challenge here is the labels for training this CNN is unknown. These labels are unknown. We only know the equation. The training data only tells us this equation is true or false. And also the logical reasoning here actually depends on the output of the perception model. So here, unless it gets the correct one, otherwise we cannot know what kind of reasoning happened here. So this is the major difficulty and challenge. So the data we have is this kind of equation. So we have two sets of data. One of them is made from real handwritten digits. And this one is some random symbols drawn from another data set. So both of them are equations. And some of them are true and some of them are false. But we do not know which character corresponds to which number or which symbol. So the output, we have to train a convolutional neural network to recognize these symbols. And also we have to figure out if it is addition or it is an XOR or it is some other kinds of logical operators. So we have some background knowledge as well. The equations are like x plus 1 equals to z. This is the structure. And we also know, well, every digit is some kind of list composed by 0 and 1. And we also have some background knowledge about how to calculate. So how to calculate it is calculate bit by bit and from backward to forward. So this is how to calculate. But we still do not know what kind of operation here. Like 0 plus 1 equals to what? We do not know this. So this is the structure. We have some machine learning model here, which learns the mapping from raw data to the numbers or the symbols. And then we have a logical model here, which can do some reasoning at this place. And then, like the historians, we have something happen in between here. We have a consistency optimization module, which tries to maximize the consistency of machine learning and logic reasoning. So this is basically what we have done. We have a neural net here to interpret each symbol, and then we have some optimization here, which tells you, so this perception is wrong, you have to revise it. And when you do a revision, you revise into the neural net and retrain the neural nets and do this stuff repeatedly, again and again, until the optimization has been maximized. So I'm going to omit all these technical stuff. So the intuition is to maximize the consistency. So we have some consistency constraint here and trying to maximize perception and reasoning. And this consistency is defined on the training data set, of course. And also when the perception model was fixed, well, you can try to recognize it, recognize the primitives. However, because the model is untrained, so it could be wrong. Then we can guess which are wrong, like the historians. And then we mark them as they could be wrong. Then we change it to maximize the consistency until we really got the maximum consistency, and then we can retrain the perception model and do this iteratively to combine them. So the good thing of this is we get rid of any gradient computing from here. So we use pure logic-based method. So there are lots of symbolic AI stuff. We can directly apply them and make advantage of them. So this is the difference between conventional supervised learning and our abductive learning. So conventional supervised learning will have instance and labels, and we train classifier. Now we have some classifier, but the labels it output we do not know. So the first time it could be wrong. Then we put it into a reasoning module and try to see, okay, we can change one of the label, pseudo label, or the primitive facts to make this thing consistent, and then retrain the classifier and do this again and again until we got the good result. So this is the output of our learning task. So firstly, the CNN actually outputs something like this. It's totally random, like 0 plus 1 plus 0. So this is not even an equation. So when we put it into the reasoning module, it tells you at least you have to revise the plus symbol here to make it like an equation. So the first time it learns how to separate from plus symbol, 0 and equal symbol with regard to any other digits, and learn some completely crap rules. These are junks, so they are fake. And well, when the learning continues, it finally can recognize all this this batch of data. So you can see the consistency here is maximized, and it learns some rules like this. So like 1 plus 0 equals to 0, 0 plus 1 equals to 0, 1 plus 1 equals to 1, and 0 plus 0 equals to 0 and 1. So this is actually completely opposite from like, so here actually is the addition rule. However, the 1 here is actually 0. 0 is actually 1. So it actually doesn't matter how they represent it in a symbolic form, but the meaning here still succeeds, still holds. So here are our experiment results. So we compared to some state-of-the-art neural nets like differentiable neural computing, transformer, or long short-term LSTMs. So these are our approaches. So we trained them with only 5 to 10 length equations, but it can really generalize very well. However, the pure perception-like algorithms like neural nets, they dropped quickly, even though they were trained with all these equation lengths from 5 to 26. However, they still dropped, the performance still dropped very drastically. And here is on the other data set. So the perception is much more harder. So that's why the performance drops, but actually still will way better than the pure perception-based approaches. And here is the training accuracy. As we can see, the perception model here can gain increase. So this is the CNN symbol recognition. Even we do not give them any labels to train CNN, the accuracy can go. So knowledge can help us to get good labels. And here are the consistency, the reasoning part. So the blue ones here are inconsistent, and red ones are consistent. So you can see when the perception accuracy is greater than 0.8, then the consistency can really happens. So perception also helps reasoning, and here reasoning helps perception. They are mutually beneficial. And here we do some model reuse as well. We reusing the perception model, so we change the equations from addition to XOR. You can see if we maintain the perception model and change the rule of addition, our approach actually quite fast, converges quite fast here. If we learn from scratch, it takes like 20 iterations about. And here is when we fix the rules of addition, but we change the symbol representing them. So they're visually different, but we have to retrain the CNN, the perception model, we can see that if we have a correct knowledge, then still it will converge a lot more quicker than learn from scratch. And well, so this is, yeah, I have to make the conclusion soon, it's pretty late. So firstly, we do not have any, we do not use any embedding or gradients in our model. So we use the full-featured first-order logic. So it has better generalization. Even if we change the symbol or the representation, the images, we still can extrapolate our model to them. And with logic, we can handle recursive knowledge, which like the how to computing digit by digit. And it also can take advantage of over 60 years of symbolic AI research. We can directly add any symbolic AI system in our model, like constraint logic programming, answer set programming, etc. Also, abductive learning is a way to connect high-level reasoning and low-level perception, and this is a fact from cognitive psychology. And also, well, abduction is finding some explanations. So abduction is neither sound or complete. That's why human and our machine need the trial and error to maximize the consistency of data in the model. And an open question is that dividing line between high-level and low-level representation is still unclear. Now we have well, in this task, we really have some good representation like 0 and 1. So this kind of things are the boundary between symbol and sensory information. However, in real task, it's quite unclear. So what we are trying to do now is trying to make machine learning more human-like. So that's why we can, we can, solving more and more reasoning problems or complex tasks in our daily life. And we have some pretty good progress here. So I haven't put it in here, so that although the task here is a toy problem I have talked, but we have tried on some real tasks like X-ray image. We can tell whether someone got ill because we have some background knowledge from the doctors. They have really specific logic rules to tell which degree of the illness are. And also we have applied it on some law documents and trying to learn how the judge make judgments, like mapping from some natural language data into some crime elements and predict the length they put the criminals in jail by considering this. So the second stage is reasoning, and the first stage, interpreting the crime elements are perception. So they actually happens all together. So we can apply this paradigm in all kinds of complex tasks, which can achieve much more better performance than the end-to-end learning way, which doesn't consider anything about reasoning. So this is a work I have recently done. So it's we just have code here, and the paper was submitted to New Rips, and hopefully it can get accepted so you can see it in the next month. But this is our code. So if you would like, you can check with that. And thank you very much.